All right, everybody, we should be live here with our interactive conversation with Eugene the Philostopher. So it's the analytical anarchist, the particle punisher, the ravishing reasoner, the monotone from Minsk. It's Eugene Bagashov, a.k.a. Eugene the Philostopher. Eugene, welcome to the live stream, and thanks for proposing it.
Oh, hello, Dan, and everyone else.
Hey there.
Well, what a bunch of how do you call them? Epithets? Do you have such a word in English?
Yeah, epithets. Yeah, that's a thing.
Epithets. Okay.
I'm not sure the exact definition of that, but yeah, something. Maybe
Okay.
maybe some stilted language. I like stilted language. It's fun. As long
Yeah,
as
it's like when a writer describes a character and they attach some specific word to their description. That's what
yeah,
it is.
I wanted to make it
What I
sound
meant.
like the intro to an MMA fight or something.
Yeah, that kind of sounded like it, so it's fine.
Cheers. So yeah, everybody, Eugene came up with the idea of streaming today. Thought it was a brilliant idea. It's always interesting having random conversations with Eugene. We're going to kind of model this one after the Joe Rogan experience, I guess. A couple more intros here. If you haven't subscribed to our channel, make sure you do it. But more importantly, help Eugene get to 500 subscribers. Make sure you subscribe to Eugene the Philostopher. It's with a T, Philostopher. And incidentally, he's the greatest living philosopher since the unfortunate passing of Robert de Nameland.
Yeah, that's true. Actually, I gotta say thanks to you because after I assume it was your intervention, almost like divine one, on my latest video, I got some insane views. So now
Nice.
it's like my third best video by views.
Sweet. Yeah, so hopefully that was a benefit. Are you at 500 subscribers yet? I know you were
No,
470.
483, something like that.
Okay, so you must have gained like 20. That's the smash-o-mash bump right there. It's
Yeah, probably. By the way, I've asked YouTube on Twitter, why do my views keep falling down after some time? And they're saying they have some system to recalculate them over time, actually. So apparently if somebody clicked it for 2 seconds, it doesn't count or something like that. Well, that was the explanation they gave to me, essentially.
yeah, that's from what I understand, you have to view a video for 30 seconds for it to constitute a view, assuming it isn't a short, because shorts, you can make them, the default setting is 15 seconds for a short. So yeah, 30 seconds, but then why would it ever register as a view in the first place until it gets to 30 seconds? Sounds like it's lip service to me, but hey, I can't see their code. Nobody can see their code, so we're forced to just take their word for it.
All right, yeah. Well,
So
since I'm kind of quasi-hosting this, let me start with a question. Can you describe, you're watching the sun probably a few hours per day. So how would you summarize a recent situation, in the last couple of months maybe? What's the solar activity levels? How are we doing in long term? Are we past the peak yet? Or are we somewhere close?
I don't think so. I think we're still over a year out from solar maximum. I mean, and part of that has to do with coronal holes. There's been a shortage of coronal holes throughout the whole cycle, dating back a couple of years. So I mean, that's a thing that coronal holes have to happen. They have to migrate across the equator. So now, although at the same time we are seeing quite a lot of magnetism here appearing at the opposite poles. So we are seeing South Pole coronal holes at the northern polar region and vice versa. But no, I don't think we're at solar maximum yet. If you look at the historic sunspot data, it looks like solar cycle 25 could exceed solar cycle 23. So, a year ago, I thought that sounded like pretty crazy talk. I heard Tamitha Skov say it, and I was like, I don't know, but could very well be. And now in the past week or so, we've seen the sunspot number drop down to 50. So, but it looks like there's a miniature. We just covered this on this morning's daily space weather video. It looks like there's a Terminator event kind of a thing going on the eastern limb. So over there on the east side, there's a lot of magnetic indecision happening over there. And one of the newer theories by Scott McIntosh and Steve Lehman is that when the magnetic fields in the northern and southern hemisphere between the equator and like 40 degrees, when those fields get extremely equivalent to each other, they have a tendency to cancel each other out. And that might be a thing that's preventing sunspots from forming. Eventually that's going to let go. That it has to somehow be related to the coronal hole process too. So it looks like a miniature intra-cycle Terminator event happening just in the past week or so. It might be breaking down now because just in the past couple of days we saw a North Pole coronal hole rapidly migrate across the equator down toward the south. So yeah, no, it's long story short, with respect to your question, I don't think we're at the peak. It could be a double peak thing where we're going to see it go back up to 200 again, but it's way too early in the cycle for us to be at the peak. And sunspot cycles are extremely consistent in their length. So the likelihood of having a really short cycle is very low, and the likelihood of a very long cycle is really low. So, just based on that statistical analysis of how long a cycle is, it doesn't seem plausible that we'd be at solar maximum. What do you think?
Mm-hmm. Well, you can look at different stats. Obviously, you can look at sunspot number. You can look at, for example, the reversal of the polar fields. Right, that's another metric. So if you look at the very top, the very pole, like let's say above 55 latitude on both poles. So when it changes its average magnetism to the opposite, you might say we're at the maximum, right?
Well, yeah,
that's one way of looking at it.
That's sort of the definition of solar maximum, right? When the fields are in a certain configuration. But you never know how strong they're really going to get. The plasma is kind of hiding that all the time. It's obscuring the photosphere fields. So, yeah, there's a lot that goes into it, but.
Well, I'm looking at the WSO solar polar field strength. I can send you the link. Though it's on Solon website somehow. I can't find it on the Wilcox Solar Observatory. They have the solar polar fields filtered by 25 nanohertz or something like that.
Yeah, I haven't looked at this one for a while.
Well, I've just sent you the link. You can look on Discord.
All right.
No, you can't.
No, I can.
Yeah. Yeah, so as you can see, the north has already reversed. You see the blue line goes below zero.
Yeah, for sure.
But the south is still not reversed. It's actually kind of, arcing downwards.
Yeah, that's interesting, yeah.
And it has been noted, I have a link. I even quote this paper in one of my papers about the flares. Actually, the only paper about the flares I have. Where this Leif Svalgaard guy and somebody else, they discuss how actually northern and southern polarities evolve separately on the sun. So It's not like a single dipole that just turns on its head. It's actually two separate arrows, if you wish. Which are slightly distinct, and you can see it with pretty much every max. But according to this, at least, you can see this green vertical line at the very end, and it says reversal N. So technically, north has already reversed.
Right. And then let's see, it'll be solar maximum when we get when we see
Both of them.
like an aqua colored line.
Reversal south, the red one actually.
I'm sorry, that's minimum. Yeah. Reversal
Yeah.
south.
So that's kind of the thing. You see this lag in the reverse, like of one pole versus the other, is what causes these double peak cycles. Because it's roughly speaking, right now we're witnessing maximum of the north, roughly speaking, and then with some lag we'll see a maximum of the south. And you can actually see it in the distributions of flares. Like I've looked at it. And you can see the first peak, more stronger sunspots in one hemisphere, and the second peak is in the opposite one.
So that is a forecast for a double peak cycle then.
I would say so. Yes.
All right.
I would say so. We might actually even judge about the length, like how much it takes for the second peak by comparing to the previous one, for example. But the dates aren't super visible. Like it's something. The green one and the red one, we need to compare them, like the dates.
Yeah, like like how much horizontal space is between those vertical lines.
Yeah. I would say it's about a year or something. A year, maybe a year and a month, something like that. 13 months. So maybe we'll see something like that this cycle too. I don't know.
It's also worth noting the strength of the fields compared to last cycle.
True.
Let's see. North peaked at, what is that, 74 or something like that. Last cycle it peaked more like 60. No, not too much higher there. Only a slight difference there. And then the south.
But you can definitely see that this cycle is shorter than the previous one.
It does indeed look shorter. Now,
but the 23 was also short.
Yeah, and shorter cycles are associated with stronger solar cycles too. Just like, and longer ones are associated with grand minima cycles.
Probably, yeah.
So, yeah, I mean, this sort of supports the idea that it might be, I think it's going to be similar to cycle 23. I think it might be a little weaker or a little bit stronger than cycle 23 in terms of sunspot number and radio flux.
Mm-hmm.
So, but I mean, I think we're definitely seeing a shortage of coronal holes because we've had almost no space weather from coronal holes throughout the entire cycle so far.
Mm-hmm.
So, I mean, maybe there'll only be one polarity. Like that, like maybe we'll see a bunch of South Pole coronal holes here for the next couple of years. I really don't, I didn't study the last solar cycle, the way I studied this solar cycle. Obviously, I didn't put 40-minute videos about it every day during the last cycle. But those coronal holes, they have to migrate. And I don't know. You really have to ask yourself, is the interstellar environment, does a less dusty interstellar environment mean a more active star or a less active star? That is the real question. If the amount of dust outside the heliosphere probably has some effect. I mean, I think when you look at other stars when they go into extreme differences in their activity, whether they get much dimmer or much brighter, it's probably got something to do with the interstellar environment.
Yeah, it could be, but then again, we're facing the ultimate question: what powers the stellar activity in the first place?
Yeah, that's true. And as you're well aware, I have a crap theory about this that I'm not going to describe in this video because that's for Gold Smash Team members only at the moment.
All right.
But
anyway, like from my research into solar flares, I can say that, like, I just can't. Like, I just don't see any immediate, like, well, at least planetary, influence on the sun. Like, it looks completely random with respect to where the planets are. And if the planets cannot influence the sun, how can dust influence it? I mean, there isn't much dust, actually. falling onto the sun. It's not that big of a
Well, I mean,
quantity.
the thing about it is the dust from the interstellar environment, it's not going to just like float around into the solar system. You know what I mean? It's going to align to the sun's magnetic field lines. So
Yeah, if
it's
it's ionized, then yes.
yeah. I mean, it's most of it is probably ionized, so it's not just going to like waft into the solar system. You know, it's gonna be oriented in very specific ways, I would imagine, based on the sun's magnetic field. So that's going to change the way it's going to react at solar minimum versus solar maximum, because at solar maximum those magnetic fields are all over the place, including pointing out the equators as well as at the poles, and they're all chaotic and they're all over the place. But at solar minimum, they're largely just at the poles, so that it's going to change the way it operates too. Whether it's a repulsive force or an attractive force. I mean, there's a lot of stuff that's pretty counterintuitive, I think, going on there with the way that a star is going to interact with stuff outside of its stellar sphere.
Yeah. Hello, Robert, in the chat.
Yes.
Thanks for joining us.
And thanks for keeping track of the chat. I do have it up, by the way, folks. I have the chat here, and I am able to. I should be able to see it. I have it on my screen, but it's not showing anything. So
I do see it, so you're fine.
Excellent. Oh, there we are. Yes,
Yeah.
Thanks to everybody who's left comments. If you want to steer the conversation, then please leave comments. Press the like button, press share, and whatever you do, don't forget to head to Eugene the Philostopher and subscribe to his channel. He's only 17 away from 500 subscribers, folks. So
What happens at 500, though?
absolutely nothing. You'll be halfway to 1,000, at which point you can monetize. But you probably want to get to like 11 or 1,200 really, because I'm not sure exactly how that works. It's been quite a while since we monetized. But hey, the good news is once you finally get monetized, your videos should get more recommended, theoretically speaking, because now YouTube does have a financial incentive to recommend your videos, put your videos on next play if people have autoplay turned on and things like that. And that's just for the viewers out there. That's the reason why content creators are concerned about getting videos demonetized. It's not because we're paid so much money for a video that it matters in any way if a single video is monetized or not. That has nothing to do with anything. Our concern is that if a video is demonetized, it gets buried in search, it doesn't get recommended, and it doesn't get autoplayed. Because if it's playing limited ads, that's de-incentivizing YouTube to recommend the content. We've had many times on our own channel, we've had problems finding our own videos. So
I usually have problems finding what was exact video where I made some point, because it's usually pretty chaotic, the things I talk about. Sometimes very tangentially related. So
well, that's part of the glory of your channel, though. That's part of what makes it so good, because you're a punk rock channel, and hey, the algorithm doesn't like that. Okay, the algorithm, our channel, we've got playlists that have like cycling videos and stuff. And the algorithm doesn't like that. The algorithm likes when you put out videos that are just in one subject matter and that's it. So it's harder to grow as a channel if you're putting out content in all kinds of different genres. But at least your videos have a pretty consistent format. I mean, they're less all over the place than ours are. I've got videos that are from the bike, from on top of the bike. I've got videos that are like live streams like this. I've got the daily space weather, now recorded videos. And by the way, we would make the daily space weather videos live. We would do them live. But the problem is that now that we've got shorts and we're seeing an average of, I think, about 2,000 views a day at this point because of the shorts, you can't make shorts out of a live video. Or at least it takes a long time for it to get encoded, so you can do this. We use the remix feature to put the shorts out. So that's the main reason why we don't make the daily space weather videos live. It would save a bunch of my time because then I wouldn't view the live premiere with our viewers. Part of the reason I make the space weather videos in the first place is because I wanted to create a video of the graphics that I wanted to look at, because the content on YouTube about space weather is insufficient for me. So I wanted to take the content I wanted to look at and put it on a bigger screen. That was the basis for the videos. Then eventually I realized that other space weather content creators that have much bigger channels than us would benefit from our videos, because we show a bunch of data that they don't show, and if they understood how to correlate that with the other bits of data, it would be helpful to them. But only Tamitha Skov knows how that stuff correlates. The other channels that produce daily space weather content have no idea what they are talking about. They don't understand basic physics. So it's...
Yeah, I actually accidentally stumbled on some, like some really weird stuff, like, kind of like vanilla astrology mixed with space weather readings, and it was kind of strange.
Yeah, there's a lot like wizardry.
The very vibe of the guy was strange, if you know what I mean. Like, it was all this kind of yoga, spirituality kind of stuff.
Yeah, it definitely gets pretty weird. I've had people doing astrological charts on me and stuff, and then I'm like,
really, on you?
Yeah, and it's I don't know. It's whatever. I mean, yeah, I guess the good news for astrologers is that cosmology is starting to look more and more like astrology nowadays. So that's sort of a cool thing, I guess.
Well, there is this thing which you've probably heard about, at least I've mentioned it many times. It's this Shnoll effect, right? Which, and I'm trying to I'm kind of semi-deliberately trying to steer the conversation into weirder stuff.
Shnoll, like SCHNOLL?
I think it's SH, not C.
Okay.
Just SH and then NOLL.
Yeah, what's that all
effect.
about?
So it's about dependence of fine statistics of random measurements, I guess you could call it, on time. So, or random processes in general, not necessarily measurements.
Yeah, but are they really random though?
Well, that's a good question, because if their statistics depends on time, and I do mean fine statistics, like not the mean, not the deviation, but like the really, really fine structure of the statistics. I probably need a whiteboard to explain it in more detail. But anyway, this statistics of random processes depends on time, which, as you rightly mentioned, if it does depend on time, it's probably not very random, right?
I think random is the most overused word in the English vernacular.
Could be, yeah. So what Shnoll concluded, and I kind of agree from at least the data that he's given, like I haven't checked it myself, and I can't actually, like I'm not doing any experiments with enough precision anyway. So what he concluded is that essentially, like how he phrased it specifically was that the picture of the sky that you can observe like influences like whatever random process is occurring right now that you're measuring. So we see the cycle related to Earth's rotation, I mean around its axis.
I see what you're saying, because there's obviously like this star field in the background, right? If this is what's overhead. There's light coming in that's causing some effects on things, even though they're very minor, but then there's also radio frequencies making it all the way to the surface. There's microwave and
all kinds of stuff.
Aspects of the electromagnetic spectrum.
Yeah.
I mean,
so all of the stuff like
cosmic
this,
rays, cosmic rays are going to be at a different level when that star right over there at the bottom of the screen and the one right above your head on the thumbnail, when Deneb is at near your zenith as opposed to scraping across the horizon like it does every morning now, of course that's doing something, right?
Vast Thinker says stick to the science. They can take their charts and stick it up their astrology. Okay.
Is that
Point taken? Yeah.
Yeah, I mean, we're not trying to make a case here for astrology, but
I mean, I kind of am, to be honest. Not vanilla astrology, though. Like I'm not trying to like seriously read what they write about the zodiac signs, but I'm just saying that modern science, at least in the face of Shnoll, shows that the picture of the sky seems to influence like the smallest processes. If you think about the larger processes, they're made up of smallest processes. Like it probably won't impact the Earth's rotation around the sun per se.
yeah, probably not.
But it might impact like the replication of a DNA, for example.
Oh,
yeah,
absolutely.
Like
it could impact things like mutations in your DNA. It could impact things like your dreams. And we know that it impacts computers, right? Part of the way processors, cosmic rays impact processor errors. So processors do redundant calculations to make sure that there's enough reduction of error to have legitimate calculations going on in a computer. Cosmic rays are figured into the framework of how computers operate because they're going to get bombarded with cosmic rays all the time. So, I mean that sounds like astrology in a lot of ways.
Yeah, and you know what is more interesting? Probably there's one semi-forgotten thing, which is called the Mach principle. Have you heard about it?
The Mach principle? No, I'm not familiar with that.
Well, the same Mach, who's like the Mach's number, the Austrian physicist.
Like the speed of sound?
Yes, that's the same guy.
Okay, what's that?
So Mach's principle states that, well, basically it's the idea of where inertia comes from. Because there is no like mechanistic explanation of where inertia comes from. We just postulate it's there, right? So anything that has mass has inertia, and therefore blah blah blah. We have Newton's laws. But what exactly is inertia? So Mach's principle states that it's actually when you're trying to accelerate something, the inertia is essentially the effect of all the universe, like trying to keep the body where it was before you tried to accelerate it. Does that make any sense? So the universe was, in air quotes, happy where the body was before you tried to push it. But when you try to push it, like it resists.
You brought it out of a state of static equilibrium, and now it wants to.
Yes, sort of. Yeah, like all the distant stars, they keep pulling on it, trying to keep it in place. That's the principle. It's just an idea of how inertia appears. So you don't notice it when stuff just moves without acceleration or is stationary because this influence is cancelled out. But you do notice it during acceleration.
It's funny that you bring this up because we've been having a conversation in our last 2 live premieres for the Daily Space Weather Show. One of our viewers, I don't know if he doesn't understand how G-forces don't happen when you're at a steady speed. In other words, if you really slowly accelerate to escape velocity, you're not going to experience any measurable G-forces, but you can still leave the Earth's gravity. You know what I mean?
Yeah, it would just take a very long time, probably.
Right, and when you get in a rocket, there's limited fuel, so you have to accelerate to these high speeds quickly in order to be able to make it to escape velocity, in which case you experience G-forces. But when you're at speed, the velocity has nothing to do with there are no G-forces when you're at speed.
Yeah. That's why you have weightlessness when you're in orbit, because you're literally free falling.
Right. Yeah.
Oh, wait, there was something else. Yeah?
When you're in a low Earth orbit, yeah.
It doesn't matter when you're in a high solar orbit. If you're in orbital motion, that is, it's only the gravity that's causing you to move. That's literally the definition of a free fall. Like when the only force acting upon you is gravity. That's
Right,
called
but
free fall.
if you go out to 5 lunar distances at at the distance of Lagrangian, 4 lunar distances at the point of Lagrangian point 1, but you're not at Lagrangian point 1, and you stop with respect to everything else, you'll still be weightless, but you're not moving with respect to the sun, earth, moon, etc.
Well, what do you mean by anything else? You can't really stop with respect to anything else. There would be something moving with respect to you anyway.
Well, that's true. Yeah. I mean, is there some kind of weird vector, Eugene, where if you go on this weird vector, you've stopped in relation to everything, and now special relativity applies to you in reverse, and your clock speeds up? Is that a thing? I've been wondering about this for a long time.
No. There is some weird direction that we're apparently traveling, and by we, I don't even mean the solar system.
I mean the galaxy.
Yeah, the galaxy, and probably more than that.
Probably the whole cluster of the local cluster
Yeah,
of galaxies.
something like that, because the speed is pretty big. It's something like 600 kilometers per second.
Yeah.
So it's like some intergalactic speeds.
The Great Attractor and so on.
No, I don't think it's towards the Great Attractor, but it's towards somewhere, and I'm not sure where it is, to be honest.
Yeah. So what happens if you stop with respect to that motion, which requires you to travel at a really high speed in a given vector? Doesn't your clock speed up? And why not? If special relativity causes your clock to slow down with respect to everybody else's clocks when you travel at a high speed, why doesn't your clock speed up when you travel at a low speed with respect to everybody else? Wouldn't that be a relative reduction of kinetic energy? Shouldn't that speed your clock up? It would be a death vector. It would be a death vector. You know what I mean? Like
what you're getting at. Yes, but the whole idea of time dilation is like, I don't know. Like, I think it's a poor interpretation of what we observe. But I mean,
doesn't the Parker Solar Probe really prove time dilation as it's traveling at hundreds of thousands of kilometers per hour? I mean, isn't it?
I don't really know how you can prove time dilation, to be completely honest.
Well, I mean, aren't all of our satellites required to sort of calculate that to know where they're actually located? Everything moving at really high speeds, doesn't this figure into their calculation of where their location is in space?
Well, I can't give you an exact answer because I simply don't know. How it actually works. Because I've heard rumors, and I will state this carefully, that the way special relativity is implemented, for example, in GPS, is not the way it should be implemented theoretically. So they have some practical workarounds around the actual problems in special relativity, which are usually swept under the rug. Well, so people just practically arrived at slightly modified version of Lorentz transformations, if that sounds acceptable to you.
I don't know. The signal has to move at light speed, or at light speed as per the medium it's traveling through. So that affects things, but also gravity affects things because it slows clocks down the closer you get to a gravitational source, but then traveling at really high speeds makes clocks slow down also with respect to clocks not traveling at those high speeds. So yeah, I don't know.
I'm fine with clocks speeding up and slowing down, but does time slow down and speed up? That's a different question.
Yeah, that's true.
And that's the question that I have problems with. Clocks, okay, maybe, because at least you can put one clock on a rocket and then bring it back and see how much it ticked.
Right, but it could be because something like the atomic vibrations in the clock are slowing down, but time itself isn't actually slowing down because you have to use a clock to measure the atomic vibrations, and if those things themselves are slowing down, then you get to the point which we talked about when we talked about our theories of everything, right? You get very quickly to the point where you go, what the hell are we measuring now?
Yeah.
Like when you try to measure light speed, how are you going to measure light speed with instruments that operate at light speed? it's quite a paradox.
Hmm. And also one other thing I want to mention, like maybe some people would be curious, you can, and I repeat, can, it's possible, build a theory of electromagnetism without photons. So light wouldn't be a particle, neither a particle nor a wave.
Okay,
Does
like
that make sense?
all you need is the baryons and leptons. In other words,
Yeah, it would be direct interaction of charged
so
particles.
just protons, neutrons, and electrons, no photons required.
Yes, exactly. It's
Uh,
possible to build such a theory. It has been built. It actually predates Maxwell's electromagnetism, curiously enough. It's called Weber's electrodynamics. And
huh.
you can, he actually, Weber introduced, you probably, maybe you've heard about his last name because it's a unit of magnetic flux, 1 Weber. But anyway, so he actually built this theory, and he had to have a constant of the dimension of speed there, which he just measured by doing experiments, and guess what? It's equal to the speed of light, but it's just some constant in his theory that that propagates that the interaction is propagating with. And there is a sort of a relativistic extension of this theory. He worked with purely classically moving charges, which means like low speeds, even though it includes the constant c, which is Wheeler-Feynman formulation of electromagnetism. It kind of builds upon Weber's electrodynamics, even though I'm not even sure they were aware of Weber's electrodynamics. But the fundamental idea is the same: that you don't really have any photons, any like waves propagating. You just have a direct interaction of one particle with another, just with a lag.
Yeah, I mean, it seems like you're sort of getting into the realm of quantum field theory here too, because you hear it all the time when you start arguing with people about particles on the internet. They say, well, there are no particles. Even protons, neutrons, and electrons are just a series of vibrations, which is sort of a valid argument because you can express the universe via particle physics or via quantum field theory. They're not really at odds with each other. You're just it's like you're using a different language to describe the same thing.
Mm-hmm. So Secret Owl in the chat is properly stating that Coulomb's law becomes velocity dependent, and that's the case in Weber's electrodynamics. And I kind of have a vague feeling that there is some different physics with all of that. Like you can probably try to gather these, branches that were forgotten at some point, like Weber's electrodynamics, the Mach's principle. Actually, curiously, Mach's principle, like Einstein stated, that it was one of the biggest inspirations for general relativity in the first place. So it's not like it's completely forgotten, but people still kind of omit it most of the time. So you can maybe gather this and like reformulate the particle physics. Because like Maxwell-Lorentz electromagnetism, it's incredibly screwed. Like it's so intrinsically bad. Like it looks kind of cool on the surface because you can build an antenna, right? And for an antenna, everything looks cool. Like you calculate the wavelength of your radio wave, calculate the energy, everything is perfect. But once you deal with particles, everything breaks down completely. The electron has like infinite self-interaction energy. And like I'm not even joking. So electron produces electric field, which then acts upon the very electron that produced it, and like it's like a self-perpetuating loop, which gives you infinite energy, and it's obviously
Hold on,
not physical.
I think you mean the photon. The photon has infinite energy.
No, the electron. I mean, the charged particles are the sources of electric and magnetic fields.
You said
So
the electron that produced the electron. I think you meant.
No, maybe like the sound broke down or something. I said the electron produced electric field,
Oh,
which
okay.
later
Yeah.
which later acted upon the same electron that produced it. But what is electric field? Well, according to quantum field theory, it's actually photons, right? But in this picture, you arrive at these horrible infinities. You've heard about this renormalization issue and things like that.
You're outside of my particle physics understanding at this point. So,
Well, but
I believe
basically,
you.
even mathematically, like the theory is very bad. Like it's just objectively horrible. Like it works perfectly for large objects, like distributed systems of charges. Like as I've said, like I don't know, some antenna or a piece of wire, right? A coil. With a magnetic field, but it completely breaks down when you're talking about particles and their interactions. So we should try to get a better theory. Otherwise, like I don't know. Like the whole concept of point-like particles is already hugely flawed in my opinion, because, well, like think about it. If you have a point-like particle, like if you consider electron as having no size, but it has certain mass, then it means it has infinite density, or what? Like it has zero volume but non-zero mass. Like it makes no sense. Like intrinsically,
Yeah,
just
no,
you know.
I totally understand. I mean, yeah, it's particle stuff breaks down once you get to the atomic level, right? At the molecular level, particle stuff makes sense because you need A plus B to make C. It's useful when it comes to macroscopic things. I want to make a thing. I have to mix these things together to make the thing. But when you want to understand the fundamental properties of the building blocks of those things, that's when it starts to get a little bit bizarre, to the point where, now, and I know you can appreciate this. It's like, oh, this is made of smaller things, which is made of smaller things, which is made of smaller things, which is made of smaller things, and it just goes on forever. You've got quarks are made of whatever.
Well, at this point, they're considered to be fundamental, but as of many times stated, I think it's garbage.
Yeah, I'm sorry.
Like you need quarks.
Subatomic particles are made of
Yeah.
quarks, but you have to get to the point where you're just like, okay, is this observable? Is this science? Is there any kind of a test that I can do to like verify this?
Yeah.
So I just wanted to briefly bring up this thing above my head here, because we have this. There's some extreme over here on the east side. You can see that blue line. That's the sector boundary crossing, and it's waving all around over there. And this looks just like the Scott McIntosh described Terminator event, which, like, in the context of him describing the Terminator event, what he means is, at solar minimum, when we see a deep solar minimum, it can be caused by fields that aren't that weak, but they're canceling each other out, basically. And they'll never continue to cancel each other out. They eventually, one's going to get slightly stronger than the other one because nothing's perfectly symmetrical at the very least. And when it does break out, it's going to produce actually additional activity, like almost like a pressure building up, but a magnetohydrodynamic pressure building up. And it's actually happening right now over there on the east side, because we look at this every day on the channel, and it's usually basically what happens is, if you see the sector boundary crossing accelerating or decelerating, it's telling you that a sunspot's going to grow or form on the eastern limb. It's only for the eastern limb. It's because stereo B is over there, and it's just slightly to the east of Earth, but it's we forecasted this enough times that this is like legit. If you see the sector boundary crossing, if you see the North Pole current sheet accelerating toward Earth, it means you're going to see a sunspot form in the south or a sunspot degrade in the north, because the sunspots will constrain the polarity of that field. And so anyway, I can just tell by looking at this that there's a magnetic tug of war going on over there, and it's actually kind of exciting because as that portion of the sun now moves into the Earth-facing zone, like we might see rapid sunspot growth in the next week. Fingers crossed.
I mean, you'll have more excuses to watch the sun than.
Yeah, it's pretty boring right now, man. I'm not just grasping for reasons, though. I promise I wouldn't do that. Here,
I stopped watching the sun in like around 2017 after this last blip of activity.
So watch, you'll be able to see. This is the last 4 days. This is the top view ecliptic plane field plot, and you see the way the South Pole field that the Earth is currently right at the east side of. See the way it's fanning out there? That's an indication that either sunspots in the south will degrade or sunspots in the north will grow, because the current sheet is going to be polarized by the field that has less sunspots in it, effectively. So if you have, in other words, if you have sunspots in the north, you'll have a south pole current sheet. If you have sunspots in the south, you'll have a north pole current sheet. And if you have an equal number, then that sector boundary crossing, it'll move back and forth until one sort of wins that war and polarizes the plasma at the equatorial plane. Sounds crazy, but we've watched it for years, and it's certainly exactly the way it works. This dates all the way back to the days when I was appearing on Electric View with Neil Thompson and Gareth Samuel and people like that. But yeah,
what do you mean though when you say like south current sheet? Like there is no south current sheet. There's just current sheet. It just separates north and south.
So the plasma in the current sheet is it's either polarized to the north pole or the south pole.
I don't really understand what you mean.
That image right there, it's showing you the polarity of the plasma. So
but this is the magnetic field. It's not the current sheet. So red, as far as I understand, is the south. So it's the field lines entering the sun. They're towards the sun, and green is away from the sun, towards like Earth in this case.
Yeah, it's south and north pole though, because those are.
So the magnetic pole is by definition a point where the field line is vertical to the surface, so it just goes straight up from the sun. Or straight down, for that matter. So the reds are the south, and the greens are the north. Or it could be vice versa, I'm not sure on this particular image.
Yeah.
And when we cross from one to the other, so the magnetic polarity shifts from towards the sun, that's the red, towards us from the sun.
Yeah.
Somewhere in between this, we should cross the current sheet.
Yes, it'll have a tendency to affect the phi angle on the solar wind. It's not going to be exactly the same as at the Earth, because that data there above my head, it's based on ground magnetometers, and then over on the left of the Earth, like the Earth image there, that's stereo B, and then to the right, that's stereo A. They have their own magnetometer, so they give us a little bit more east to west range on it. Mm-hmm. But you can actually use that to forecast sunspots.
Yeah,
because
probably.
That will show us changes in the magnetism before the sunspot's visible. Like you'll be able to in other words, like if the southern hemisphere is extremely stable, but something starts to happen in the north, you'll see that red portion will fan out. We'll see additional. That current sheet will get, that portion of the polarity will get bigger.
It's called sector, right?
Yeah, exactly.
Magnetic sector. Yeah.
Yeah, I mean it's a south pole sector.
Yeah.
And then north pole sector's coming. It will generally affect the phi angle. The phi angle will. what did you say? North Pole is toward the sun, and South Pole is away from the sun, I think.
No, south is by definition goes into the body, and north away from it.
Right, that makes sense. Yeah, South Pole, negative BZ. Right, yeah. So anyway,
it's not exactly BZ. Like what we see here is the well, like roughly speaking, horizontal plane, right? But BZ is the vertical one. BZ goes into the picture and out of the picture. Oh, yeah, that's right,
because Earth's field is almost perpendicular to the ecliptic, so...
Yeah, well, 23 or something degrees, but for the sake of simplicity, we might say it's just vertical here. I mean, towards or into, yeah.
Yeah, but that is, that is one of the most important pieces of data there. Like, it's pretty hard to forecast a sunspot growing or shrinking or a new one forming or a new one rising. Part of the reason I never look at the helioseismography data is because I want to use that. It keeps me sharp. It keeps me able to use that because this is actually, in a lot of ways, a better forecast than looking at the helioseismography, seismology.
At some point, like in, again, 2018 probably, I've spent, like back when I was studying earthquakes, another failed research. Like I looked into all kinds of stuff, and one of the things I looked into was these SSBCs, so-called solar sector boundary crossings. So that's the moments when we get from red to green or back, right? Because somebody told me, again anecdotally, that somebody else told them that they could correlate to earthquakes. Well, they're not. Like I've looked into a huge archive of SSBCs, and I've plotted it in my program, and I tried to find a correlation to like magnitude 5 and up earthquakes, and I found nothing. Like they are completely random with respect to each other.
I mean, it's part of the nonsense when it comes to space weather on YouTube. There's a channel out there that has been claiming for years that they can look at the sun and see a coronal hole and forecast earthquakes from it. I mean, you know who it is. I'm not saying the guy's name, but there's even a paper that didn't pass peer review that even his own statistician said, yeah, the stats don't show that at all. I mean, we heard that years ago when we first started making the videos, and I've been looking at it the whole time, and no. You definitely cannot go, oh, there's a coronal hole facing the Earth. It's earthquake time. That's as idiotic as saying Jupiter and Saturn cause earthquakes. It's just, no.
Yeah, by the way, one misconception about negative BZ that people have, like I've seen this in explanations of, space, like popular science type of explanations. They're saying, well, negative BZ means that the solar magnetism is opposite of the Earth's BZ, right? I mean, Earth's field. Because roughly speaking, Earth's field is upwards, so it's positive on the Z-axis. The solar is downward, so it's, minus on Z-axis. That's why, like, the solar plasma kind of is attracted to the Earth's field. Have you heard such an explanation?
I have not heard that explanation, but by all means, explain.
Well, the problem is it's completely reversed, actually, because our North Pole, i.e. the place on the planet where the lines exit the surface, is in Antarctica, actually. It's in the south. So our magnetic north is in the south, and our magnetic south is in the north. That's why the northern end of your magnetic needle, the compass, shows to the north, because it's attracted to the magnetic south. You know? And
that's why the negative BZ induces current, because it's not a pushing. It's not banging into the field. It's getting pulled into the field instead of like a repulsive force.
So what I'm getting to is negative BZ is actually the direction of the field of the Earth itself. So it's when the Solar winds.
It pulls material in as opposed to wanting to repel material.
Well, what you effectively get is, imagine if the Earth's field was a magnet. It would be like if it was a compass needle, let's say, it would be pointing downwards, like to, the point would be towards Antarctica. And the negative BZ solar wind field is the very same needle oriented in the very same manner, like downwards. That's what I'm saying. So this explanation of attracting the opposite polarities is completely wrong. It's exactly the reverse.
Yeah, it's a pull versus a push. When you have a negative BZ, it's like a pull, and when you have a positive BZ, it's like a push because it's repelling the magnet versus attracting the magnet.
Yeah, but in reality, like you have to look at where the particles go, because well, it's actually very complicated. The structure of electric currents around Earth is very complicated.
Yeah, because the particles are orbiting the magnetic field lines.
Yeah, that's true, but there's, as you can see, there are two different magnetic field lines in this particular case. It's the Earth's and the sun's, the solar winds.
Right, and the BZ is a reference to the sun's, because that's why we have spacecraft out at L1, because you can't measure the sun's magnetic field lines via the solar wind from inside the magnetosphere. It's too weak to be measured from the Earth side. Got to be outside the magnetosphere.
Yeah. Well, anyway, like fundamentally, what's the difference? I mean, what's the reason for the magnetic perturbations? It's the electric currents, right? So we have this so-called ring current that flows around, I think, something like 6 to maybe 10 Earth radii from the Earth, and it's roughly in the equator. So it's like a very big disk of electric current, and when it enhances, the current itself produces the magnetic field of its own, and that's what perturbs the Earth's magnetic field. So that's the fundamental explanation of the magnetic storm. It's the enhancement of current systems around the Earth through the influx of solar plasma, like however magnetized it is. And this enhancement of currents creates the perturbations of magnetic field.
So maybe we should address some of the questions here in the comments. For example, increase, like Secret Owl says, increase in cosmic rays when negative BZ. I think it's the opposite. You're gonna have a decrease in cosmic rays with a negative BZ because you'll have more geomagnetic storms with a negative BZ. Although, here's an interesting one that Tamitha Skov brings up all the time. If you have a really strong coronal mass ejection impact with a positive BZ, it induces an electromagnetic pulse at the bow shock region, because it's that repulsion. It's smashing into it instead of being drawn into it like a current. It's being smashed into it instead, causing an electromagnetic pulse, which is, that's not what happened at the Carrington event. The Carrington event had a strong negative BZ, most assuredly, because it created really strong geomagnetic storms. But there was a thing that happened in the early 70s that was a really strong impact, but it didn't really create geomagnetic storms, but it set off landmines. It set off, not landmines, underwater mines in the Vietnam conflict because of the electromagnetic pulse that was emitted from the bow shock region. So, that's the anti-Carrington event. And that's what a lot of people don't seem to realize, that the Carrington event has to be a very specific thing. If it's not a strong field and a strong negative BZ, it doesn't do the same thing as a Carrington event at all.
Well, various parameters of CMEs have different, how they call it, geoeffectiveness, right?
I mean, even what time of year that it hits, if it's around the equinox.
Sure. Yes. So if our poles are tilted towards the sun, then definitely it's going to be better for the storm, rather than away.
If it's
not away from the sun, but more like sideways.
Yeah, around the equinox.
Yeah, that's where they're tilted towards the sun.
Yeah, so like if we're gonna have a crazy Carrington event kind of a thing, let's hope it happens around the solstice, because it's less likely to take down huge portions of the power grid.
Wait, I'm actually wrong. During equinoxes, we're tilted sideways, and it's actually not our tilt specifically. Like,
it's the angle of attack of the solar wind with respect to the magnetic to the axis of the axis of the magnetic field of the Earth. It's called the Russell-McFerrin effect.
Yeah, but I don't think it's even that. I think well, it could be that actually. Like if you draw the Parker spiral, it will kind of make sense that
the first thing that happens is, like, the mechanism that starts things out with the Russell-McFerrin effect is the acceleration of electrons in the outer Van Allen belt. That's the first thing that happens. They come out to meet the incoming solar plasma.
Mm-hmm. Well, anyway, another factor is our tilt, the tilt of our orbit with respect to the equator of the sun itself. So during solstices,
but that's because the plasma comes out of the sun mostly at the equator.
I would say it's more because of the polar coronal holes. Like, look, if you look at the sun, well, right now we're relatively near the equinox still, like a month and a half away. Actually, a month, right? But it's not the equinox exactly. It's like more the September 8th or something is the date when we are kind of the highest above the solar equator. And we see, like, the North Pole, effectively, when we look at the sun, it's slightly tilted towards us with its North Pole. So we see more of its North Pole in the north. And in the spring, it actually tilts kind of backwards, and we see more of its South Pole, if that makes sense.
Oh yeah, you'll be able to see it better from the 211 angstroms wavelength.
So yeah, if you speed up some video of the sun, you would not only see it's changing in size as we move closer and farther away from it during the year, but you will also see it tilting kind of away and towards us. So on September 8th, around so, like, I have to look it up, we're at the highest point in our orbit above the solar equator, and the difference is about 7 degrees.
And then at the end of March or something?
No, the beginning of the March. It's exactly halfway, half a year apart. Well, not exactly. I mean, our orbit is elliptical, etc., etc. Maybe a difference of a couple of days here and there.
Right.
Then we don't exactly have equal years, right? We have 365.25 or about so. So it changes from year to year.
So yeah. Should we like completely change subjects? And
well, you wanted to answer more questions, we can still do that.
All right. What do we got? We know the sun affects every planet in the solar system, and there's a correlation between their weather and activity and the side facing, and we know who you're talking about in the end. I don't have any idea what you're talking about.
Well, I wish we knew which side we're facing, but I have doubts it's the front side, if you know what I mean.
I'll tell you what. One of the most interesting things that I've heard anybody say, it's with the amount of information that I've amassed about the sun over the years, one of the most interesting things I've heard anybody say, what came directly from you, because you said something really bizarre, that is it 2 different locations that are sort of fixed on the sun, where sunspots are more likely to form over decades?
Yes, yes, that's the
Rotation
case. Yeah.
after rotation.
Yes,
Is
yes.
it just two spots?
Well, kind of like two areas,
Yeah,
two
yeah. So
general areas.
two
Like
little.
if you look at this central coronal hole, you see the kind of a vertical-ish one right now on your screen.
Yeah.
I would imagine it's something like that in size.
Okay. Yeah, but
Maybe slightly bigger.
that's a crazy thing. I mean, that's like yet another thing that suggests that there's some kind of solid central core. I mean, it's proper blasphemy. You've it's we have to get Scott McIntosh on one of these live streams, because he already considers himself a blasphemer, and when you start talking about things that most heliophysicists will just be like, oh, I can't get into that realm. He's on board with it, like one of the things that I brought up one time was because I was talking to him on a Zoom call, and I'm bringing up this is the 1600 angstroms wavelength, which depicts ionized carbon, and it's like, dude, where is all that carbon coming from? It's it's getting made right there. So, like, that's blasphemy. It's right there in the SDO every day, but that's somewhat controversial in the realm of heliophysics, because no, heavy elements, metals are being made right on the surface of the sun there. It's crazy. Like, how is that? Apparently that's controversial.
I mean, not really. They have in mainstream, they have the so-called CNO cycle, carbon, nitrogen, oxygen, which is kind of acknowledged. So you can kind of recycle these elements back and forth.
Well, that's true. I mean, there's obviously there's fission and fusion going on.
Yeah.
So,
Yeah.
All right, that's true. But then what about all of that iron, Eugene? What about all the iron? Right? There's one of the many different species of ionized iron that we show all the time in the channel. There's 94 angstroms.
Well, supposedly it's the supernovae, man.
Oh, so all that iron, it was just floating around in the solar system long before the sun ever formed, right?
Yeah, kind of. Well, I mean, I just FYI, I'm saying this sarcastically. So
No, I mean I'm saying that's the accepted concordance model of stellar evolution, that the iron, it's not being made there, it was there in the first place. Or
yeah.
something. It's blasphemy, Eugene, blasphemy, which is, by the way, the only thing that advances science. Because if you remember, Galileo suggesting that the Earth orbits the sun instead of vice versa was blasphemy. The Catholic Church didn't like that.
So there are, returning to your question, these so-called active longitudes, which produce most of the active sunspots, and they persist. Yeah, they're actually more sturdy than coronal holes. They exist for decades. But I mean, you can't really get anything like that from any external source, because why would they rotate with the sun then? They should be like fixed to the stars or something.
And how would they be there if the star was made of a gaseous plasma? If the internal portion of the star was a gaseous plasma, how would you have these consistent spots? In fact, I mean, well, let's face it. How would you have these consistent solar sunspot cycles? It's like the idea that stars are made of a gaseous plasma is as silly as the idea that stars are electric and rely on a Birkeland current in order to be as stable as they are. It's just ridiculous. Like, the reason I don't believe stars are electric is because you're not dead. In order for it to be stable enough to sustain life on Earth, how could it possibly be relying on a Birkeland current? Like, where is it? Like, why don't we see it? Like, what? It's as silly as the galactic current sheet idea, right? Like, if there was a galactic current sheet, every galaxy that we looked at would have like concentric bright rings, and we see
that there are current sheets in the galaxy. I mean,
for sure.
There's no doubt about that.
For sure.
I mean, like, look, it's basic plasma dynamics, right? What do we need to have a change in magnetic field? We need an electric current, which means that in between two regions of different magnetization, whatever they are actually, wherever they are, in the plasma, there should be a current running.
You don't need electrical current to have a change in the magnetic field. You could have,
yes, you do.
You could have insulation.
What?
You could have a bunch of dust in the way that's... I
haven't seen a Maxwell equation that would include dust. I've seen the equation that links magnetic field to a current.
Okay, so
that's what I'm saying.
But okay, so like that image above my head right there.
Yeah.
Look at the bright spots. Like the bright spots kind of like in the center of the disk. Why can't we...
You mean the sunspots? Right?
Yeah, the plasma in the active region. That's what you're really looking at, the UV from the plasma, okay?
Yeah.
Why can't you see the photosphere there? The plasma is in the way, preventing you from seeing the photosphere. Charged particles are going to obscure your view of a thing.
Yeah, or maybe it's just the photosphere is not emitting UV, but this thing does.
Well, I guess you could say that. Yeah, you could say it's not emitting UV, but...
Well, you can see that the deeper you go, the blacker it becomes, so the emission is really low at the photospheric level, but it's higher if you're slightly above it.
Is it? Then why do we see more large solar flares at the limbs?
Good question.
I appreciate you're playing devil's advocate, though. That's good. I like that.
Well, I'm not. I'm actually serious. Like, look at this dark region in the north. Like, it looks that it's closer to deeper, so to speak, and it's almost completely black.
Yeah,
which means that whatever it is there is not really emitting that much UV.
In those wavelengths.
Yeah.
Yeah, I mean you're definitely seeing like deeper down, closer to the chromosphere and photosphere level, but it's like the only time you're really seeing the photosphere is when you look at the continuum and see a sunspot. Otherwise, you're not really seeing the photosphere. There's a bunch of charged particles that are preventing you from doing that.
Perhaps. Yeah.
Perhaps.
Well, we started talking about current sheet, but I forgot what. Galactic current sheet, right? So,
there's definitely a current sheet. I mean, if you get close to the galactic core, there's all these crazy bright blue stars that are orbiting the galactic core in crazy elliptical orbits, and they all have their own polar field emissions. So they have their own radio jets. They're all blasting out radio jets in all these different crazy ways. There's a current sheet there, but it's probably shaped like a sphere. I mean, the Milky Way galaxy has galactic jets, and they're like at an angle to the galactic plane. That's the net current sheet of the, the net current sheet of the galaxy is probably somewhat perpendicular to those jets, but at 26,000 light years, we don't have a current sheet from the galaxy here. I mean, it's ridiculous. The local interstellar environment is filamentary, like you've said on your own videos. There's
there's a local interstellar cloud,
the local interstellar chimney, and so on.
The chimney is like about 600 light years in size.
It's like a tube-shaped, hourglass-shaped,
but
tube-like feature.
Yeah, but this is a current sheet, like this tube.
Well, it's like a current sheet
because it is a current sheet because it separates regions of different magnetization.
Oh no,
one is inside the tube, one is outside the tube.
It is, but it's not a galactic current sheet emanating out of the core of the galaxy like the sun's current sheet. It's structurally it's nothing like the solar system.
Well, that's exactly my argument against the idea of the galactic current sheet, is that we have a lot of current sheet around us, and none of them seem to be perturbed by some mysterious wave incoming from the center.
Well, I mean, I think about it this way, Eugene. If if there were these pulsations coming out of the galactic core all the time that just reverberate across the ecliptic plane of the galaxy, right?
Yeah.
Wouldn't that happen in some other galaxies? Wouldn't we see other galaxies that have these concentric circles of bright regions around them? We see that in exactly 0 galaxies. Not like occasionally there are like a dozen that we see. We see 0 galaxies like that. Now, there are galaxies that have like a bright ring around the exterior of them, probably associated with some kind of a galactic merger, where it's like sucking in the outer portion of another galaxy, and it's like exciting the stars on the edge of the galaxy. But we see exactly 0 galaxies with these concentric rings that ought to be the case.
That's actually a good point.
It's like the flat Earth, like the galactic current sheet idea being in charge of solar cycles is like the flat Earth of cosmology.
I mean, I would call Big Bang a flat Earth of cosmology. But...
Oh yeah, no, that's a rough one. Like the cosmic microwave background, I'm not convinced of this. It's
me neither.
There's all those stars behind me there. Okay, right there, behind my head, right there. No, this side. There we go. See that? That is radio galaxy Cygnus A. Okay, it's believed to be 500 million light years away. That galaxy is the second brightest radio source in the entire sky. So imagine how many microwaves are coming from all the stars in the Milky Way, much less all of the galaxies outside the Milky Way. There are microwaves coming from all these different directions. How can there just be a weird signal that's just coming out of the fabric of the universe itself? I don't even understand the physics behind this. What kind of sense does the cosmic microwave background make? I could not understand it in the mid-90s. I don't understand it now. It makes 0 sense to me. How is empty space just... The Big Bang is just still emitting microwaves because reasons. It doesn't make the slightest bit of sense. What say you?
Well, I mean, I understand the idea. I just don't agree with it fundamentally.
But how? How could this exist?
Well, I mean, supposedly the stuff was highly ionized first, and then it recombined, which means that, roughly speaking, atoms were formed from isolated ions and electrons. And when an electron gets bound to a proton, or an ion in general case, it emits a photon. So these photons that were emitted during this epoch is the microwave background. They used to be X-rays or even gammas, but since the universe, in thick air quotes, expanded, the photons got stretched as well, and they became longer, and they became microwaves instead of X-rays. That's the regular story you will get. So the stuff has flown apart long time ago, and now it's neutral stuff, mostly. I mean, okay, you could argue that it's still ionized, blah, 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 but nevertheless, this light still wanders the universe, supposedly, back from that epoch of recombination, as they call it.
It still wanders the universe? What?
Yeah.
It just...
Well, I mean, it gets like absorbed and re-emitted and reflected and refracted, and all kinds of stuff happens to it, but yeah.
But all the stars and galaxies and many nebulae, just basic dust is emitting microwaves. Isn't that a more plausible explanation for all the microwave radiation that we see around everywhere? All you're doing is saying the average frequency of microwave radiation within this frequency band is X. It's like, so? Like, the average color of light coming out of stars and galaxy is a full spectrum white light. So? It's being produced by condensed matter.
So yeah. What they do is, and actually, like you are correct. In fact, the universe is the brightest in microwave range. Like it's actually like, per unit of wavelength, it's the densest in terms of energy in all of the spectrum.
Yeah, I'm sure. If you took all the radiation and said where, it's not too hard. Here's the peak. This is like the this is the most flux density we get among the entire electromagnetic spectrum, from ultra low radio frequency up to petatrons, which are the part above gamma rays or something.
Mm-hmm. And so what they're doing is they're measuring microwaves, and they're trying to remove all the noise, which is actually
Mainly
the
the
stuff we
galaxy.
can observe. Yeah, like the actual objects, they become noise in this case, and we're trying to find there this mysterious signal.
Yeah,
Firstly, we calculate that its temperature should be like 60K. Then we recalculate it's maybe 40K, we don't really know. Then some guy detects 2.7, and then we recalculate and get 2.7 as the result of our prediction, in thick air quotes.
Secret Owl says if you look at the CMB map, it looks like a map of the world. He should say that the Robitaille, that'd make his day. It looks like a map of the Pacific Ocean, interestingly. Who would have thought?
Does it? I don't know.
It probably does. It probably does. I'll bet there's a cyclicity to Earth's rotation, since 1/3 of the planet. In other words, I better not say it, but like 1/3 of the planet is covered by the Pacific Ocean, so water emits a lot of radiation, and hey, look, gravitational lensing. See, look right there. Oh, that's going to make somebody mad. See those blue areas right there?
Mm-hmm.
It's lensing of some kind.
Yeah.
Could be caused by gravity, Eugene.
Yeah.
Or maybe it's caused by the Faraday effect. You're going to say no.
It doesn't have anything to do with light per se. It just rotates its polarization, not where it's coming from.
All right, fair enough. I don't know.
Like, it doesn't affect the trajectory of light. It just affects its intrinsic property, which is polarization.
Okay, all right, fair enough. So should we talk about angels and demons now also, or?
Yeah, I was thinking about throwing some more spicy stuff. Like, we already talked about the elements being produced on the sun. So, and recently, like, I became absolutely convinced that so-called cold fusion is a thing, or transmutation of the elements. And like, I can easily see it happening on the sun and in like general metallic lattices on Earth, and perhaps in other conditions. But the metallic lattice seems to be like the closest for practical implementation at the moment. The technology.
God. I can't believe you've said transmutation, and cold fusion. So. Yeah. It's a good thing you haven't gotten your PhD yet, because you're never getting one now. Somebody's going to listen to this.
I mean, I don't care. Like, working with academia is a hindrance today. Like, you can't.
No, you're
do
right.
anything
You're right.
There, like
I know.
A swamp.
I'm just giving you a hard time because you're my pal. So
Okay.
I'm required to do this. This is a right of. This is hazing. No, it's not hazing. I can't make you chug beers.
Yeah,
but I would.
So I can actually fairly easily explain to you how it happens within the metallic lattice, and it's not a big deal.
It's lattice confined fusion.
Yes, it's exactly that, and it's like a relatively decent term, because even NASA uses it.
Because it holds the material in place sufficiently that when you smash stuff into it, it causes fusion.
Yeah, basically, it's kind of like. We're past like an hour 30, so I can say bad words here, or can I?
No, don't.
I can't? Okay.
No.
Okay, so, there's this saying, if you put people in a closed room, at some point they will start having S.
Yes. Yes, they'll
three letters.
they'll
word.
start having relations. Oh, hey, check it
Yeah,
out.
relations.
Never mind. The video's already been demonetized. So
Oh, okay.
I just checked. I'm looking right now, and yes,
Okay.
yes,
And so
demonetized.
I believe the same thing. I mean, it's kind of not only my thoughts about this, but kind of a common explanation that if you just stuff enough deuterium or hydrogen even in between the atoms of the lattice itself, like at some point it's gonna fuse because it just has nowhere to go anyways. So you can explain it like semi-phenomenologically through Heisenberg's uncertainty, that since the uncertainty in its position becomes very low because of the confinement by lattice, the uncertainty in its momentum rises a lot, which allows it to overcome the Coulomb barrier more efficiently. So that's another explanation.
Have you heard Robitaille's statement? I mean, he said this to me. I don't know if this is like a common thing that's said, but what he said was, he said, if mankind can harness lattice confined fusion, it will change the course of human history.
I mean, it does. Like, if you ask me, just on a like almost artistic level, I would say it's still pretty dirty. Like, I imagine there would be a much better technology one day, but it definitely does work. So
you're right. It's not precision because you're still not really. You're not in control of it. You're just reducing the randomness a little bit, right?
Yes. And what's good about
you're reducing the randomness. You're making the apparent randomness less random because you're confining it.
Yes, exactly. But the doubters usually say, well, if you have deuterium fusing there, and that's kind of the part that many people are missing, especially the, how would you call it? I don't know. Amateur experimenters who have their own cold fusion devices, they don't know it. Like what happens, what exactly happens during this fusion. Because what should happen is when your deuterons fuse, or your helium-3 fuses, or whatever, you should have a pretty powerful radiation coming out, let's put it this way.
Right.
You will have some gammas or something, which are very, very harmful. They're like few MeV, few mega electron volts gammas. And this is very bad for your health, right? So usually people say, well, if you have fusion, you should have gammas. You don't have gammas, therefore you don't have fusion. But the thing is that it's only, well, let's say we postulate that we should have gammas necessarily. But it's a wrong postulate.
You would build a
wrong statement.
You would build a Chernikov detector to determine whether or not you have fusion, so that you can detect the gamma.
You can just walk around the apparatus and see if your Geiger counter clicks or something.
Yeah.
But why don't we? The beauty of it is that we don't have this radiation, at least not in every setup. Maybe in what NASA does, they do have, but they do it in their stupid way. So they're actually kind of doing it wrong, but nevertheless. We don't have it because the energy that is usually given to the gamma in, let's say, thermonuclear fusion, where you just bump stuff together, well, it doesn't have anywhere else to go, so it just transforms into gamma and flies away, right? But when it happens in the lattice,
it ionizes other stuff, right?
No, it's directly transferred to the lattice itself. It transforms into the vibration of the lattice itself directly, and it's insane, actually.
The lattice absorbs it, and then the lattice starts emitting more radiation itself.
It doesn't. It's technically, the term used is phonons. So these are quanta of the vibration of the lattice. So it's literally just about 1,000 or maybe 10 or 100,000 of atoms of the lattice start synchronously vibrating. That's where this energy goes to.
Okay.
That's usually emitted as a gamma in a chaotic.
It's going to warp the lattice, I would think, too.
Not by much, no.
Okay.
I mean, the energy is very small if you spread it out like that.
I mean, won't it also won't it break apart some of the components of the lattice by, causing fission? It'll cause fission in the lattice too. So the nucleons that are the lattice structure, won't it destroy some of those and make those into different atomic components?
I mean, theoretically, you can have hydrogen fusing with the metal of the lattice itself.
So
That's what Andrea Rossi, for example, claimed in his ECAT experiment.
Hey
That
man,
he had
I'll take your
nickel.
word on it. I don't know. That's
Yeah, so he had nickel, whatever rods, or I don't know if it was a powder or whatever. He had nickel and just hydrogen, and it apparently, supposedly, according to him, turned into copper. So that was like the metal itself fused with the hydrogen. But I don't know. Maybe it did. It would kind of make sense, because why not?
So I've got a crucial idea for you here.
Yeah.
How about an intermission? Because I need a bathroom break big time. And
Okay.
so give me a minute and a half, and I'll be back, and I'll be as fresh as a summer's eve commercial.
Okay, I'll read some chat while you're away.
Perfect. I'll be right back.
Uh-huh. Yeah, so Secret Owl says, I'm so lost when I listen to Sky Scholar. Well, he's actually fairly clear, though he's very technical at times. So yeah, you can get lost sometimes. It's not even school level of physics. Sometimes it's actually highly technical physics. So at least I don't know, second year of university or something like that. The series Loki explains it well. I'm not sure what you're talking about, Fairy Godmother. It was probably half an hour. The discussion was half an hour ago when you mentioned this. Refining the same word. Yeah, Sky Scholar's idea is that Earth's oceans are the source of the so-called cosmic microwave background. Indeed. Astronomy is the backward state of testing our eyesight. Well, you know how these ancient tribes were testing the eyesight by how many stars you can see in the Pleiades, right? Yeah. Yeah, so Dan would probably not approve of this, Secret Owl, but he's coming back. He will probably hear what I have to say here. But I am completely convinced that transmutations, just like I've described, are happening in geology as well. So basically, Earth is a factory of producing heavy elements on its own. Because, why not? Actually, if you look at the graphs, so the effectiveness of this process of implantation of hydrogen within the crystal, it's severely elevated with pressure. So under high pressure, that it's just stacked with hydrogen, like any crystal you have. And there's a lot of hydrogen within the Earth, in various forms. So you will get fusion inevitably in these conditions. When you're 400 kilometers beneath the surface, where the pressure is, well, I don't want to give you the number, well, very big, let's put it this way. Then you'll get transmutations there, fusion. And that could power the Earth itself intrinsically. It's not just fission of uranium that we've stacked from these hypothetical supernovae that were exploding all over the place before we were formed.
I'm actually not muted. I was just screwing around.
Okay. So I was saying that the same transformation of the elements can happen geologically within the Earth, as within the Sun as well. And so we come to this another spicy idea, right? Like,
Yeah, let's do it. Spice.
the planets and stars are kind of alive, right? They kind of produce complex things out of simpler things.
Think about the solar corona or the Earth's hydrogen cycle. Is it really that different from what a brain is doing? Right? A brain is a series of on-off switches. So
I would say it's very different from what brain is doing, to be completely honest. But
all right, it's very different, but it's
yeah, but there is something to it, right? Like I've written to you. I won't repeat here what I told you like on Discord like a month ago or when we talked. But I have strong suspicion that gravitationally bound systems, like specifically that, gravitationally bound systems, whether it is an Earth as such, like as a single object, or an Earth-Sun system, or the Sun itself as such, they do kind of exhibit properties of living beings. Like not in a simple way, but in some abstract, weird kind of way.
Yeah,
because they do demonstrate what, like differentiation, right? You have different layers. Always, they demonstrate like collection of stuff, so it's almost like we're eating something. The similarities are plenty. Actually,
they might be able to reproduce. They might be able to somehow like combine or something. They may. This is one I brought up just a couple days ago. If stars are conscious, how do they communicate with each other? Right? So, and when I say that, it's because if you were a star, right, you might find humans to be completely irrelevant. You might be having a conversation with another star right now, or even another galaxy right now, right? You might be talking to a pulsar in a different galaxy via electromagnetic radiation that takes millions of years to arrive, and you're sending messages back and forth, or something like this. If you were a star, how would you communicate with
humans?
Well, I mean, that's what I really want to know. But more fundamentally than that, if stars are conscious, who are they more likely to be communicating with? Each other or humans? Of course, each other. So how are they doing that? That would be an interesting thing to figure out, right? Because if you figure out how they're communicating with each other, you'll be able to figure out how to communicate with them personally. It could be, valid. It could be important, because if stars are conscious, they're kind of big and they're kind of in charge of what's going on in the universe, more or less.
Or maybe stars are just the eggs of the supreme life form. And when they explode, that's when they hatch,
Yeah, exactly. And maybe planets are just simply stars that have kind of burned out and formed a bunch of crusty material on the outside of them.
Yeah, or not yet,
Not yet formed into a star, yeah.
Wait. What's the word? Not yet fertilized, if you wish.
Yeah, or incubate. Yeah, exactly. Yep. Yeah, it could be.
Look,
less crazy ideas.
I have one more idea, which is actually not that crazy. Look, continuing this analogy, right? What you said about the different time scales, that the sun may not even notice us, right? Because it's so slow in some sense. Well, that's actually kind of a general pattern if you think about it. And it's specifically related to scale, both in terms of time and in space. And what do I mean by that is that things that are larger than us are usually kind of look deterministic and predictable for us, whereas things that are smaller than us in size, like in scale, temporal and spatial, they look kind of unpredictable. That's kind of the general point I have. So, for example, for particles, you have again all this randomness and uncertainty. But with planets, you can calculate them with good precision, right? Their motion, their behavior. And so maybe by the same token, for the sun, we look completely unpredictable and almost like a blurry blob, like an electron cloud. which it doesn't even know where they are, where we are, rather. To some
And
degree,
also,
right?
the way that you relate to these things, right? When you're like, if you look at a stock chart, like take a stock chart of Alphabet, and look at the stock chart of Alphabet over the last 24 hours. And then without having done any previous research, just look at the 24-hour chart and then go, does this mean the stock's doing well or badly? And then look at the 1-year chart, and then look at the 5-year chart, and then look at the entire data set. When you're looking at a little piece of a graph and you don't know what the rest of the graph is, that little piece of the graph doesn't necessarily give you any idea.
Okay, I think I finally got you. Can you hear me?
Yeah. There was
Okay.
I think that was on either our end or on YouTube's end. I saw a big blip in the
Hmm.
anyway.
I think it's a good place to end, actually.
Did you hear what I
We
was
can,
saying though about how if you're looking at
yeah, they are different time scales of a chart, like a stock market or whatever.
yeah, oh, you want to close it out?
Yeah, I think so. It's getting pretty late. I think we've had a pretty decent discussion. We didn't talk like about politics and other spicy stuff like UFOs, but we talked about at least some of the spicy
Yeah, I mean,
stuff.
I think we should do this more often because
Cool.
I think there's
Yeah,
a
maybe.
demand for it, and and not just science topics. There's definitely there's a lot of stuff that I'm thinking about on a regular basis that has nothing to do with what you'd call I mean, I guess you could say it's still science because it's like going through somebody's brain or something, right? But yeah,
I mean, if I have an idea that could be formulated scientifically, even if it's crazy, well, I call it speculative science because it's just crazy, but it's still science. But if it's not, then well, it's just philosophy, metaphysics, whatever. I'm fine with that as well.
yeah, but
Could be religion even.
you could even make the argument that that's still an aspect of science because, like, psychology, if it wasn't for the way the brain works, you wouldn't have things like metaphysics and psychology, right? Even
Uh,
this could be, you could.
well,
It's like
I don't
physics.
know.
Physics controls everything, and
No, I don't think so. I think like it's just an interpretation.
well,
It's
yeah,
just like
yeah,
your
that's true.
opinion, man, this kind of approach. I actually kind of grew to detest these super reductionist physicalist explanations of everything. I think they're missing like a lot.
Yeah, stuff is pretty complicated. I mean, that's for sure. Stuff is pretty complicated, and it's like the more interesting the stuff is, the more complicated it is. The more complicated it is, the more interesting it is. You just find yourself in a rabbit hole. It's like the sport of cycling. You know, it's if you know nothing about the sport of cycling, it might seem very simple. Oh, just pedal faster, and you'll end up crossing the line first, not realizing that the fastest, smartest, and strongest guy often loses the bike race.
Hmm.
Anyway,
Well,
we should certainly do this more often, though, because you came up with the idea to come up with this to do this stream, and
yeah.
I think they should continue on some kind of a semi-regular basis. Oh, and also
Yeah.
on that note, viewers, our daily space weather show is changing starting tomorrow. There will be probably no video at all in the morning, and the daily space weather video is moving to like 7 p.m. Eastern time. So it's the format's not going to change very much. We're still going to cover the same stuff. The meteorology segment, we'll be able to use the visible satellite instead of the shortwave radiation map to show clouds and fog, right? So there's some differences happening, but it is essentially going to be the same content, give or take. Of course, our Smash team members are to thank largely for this because you've created incentive for us to continue making the content. But that said, Make sure you subscribe to Eugene's channel, or we will find you, and we will shame you. So lest your soul be cast into an ever-deepening and darkening abyss of crappy-ass content on YouTube, go watch Eugene's videos. All kinds of interesting subjects that you may have never even thought about over there. And by the way, I heard Eugene tomorrow is going to be playing chess with demons.
What the hell?
Is that not true?
I don't know. Maybe they didn't warn me, but they told you somehow. I don't know.
I heard it through the grapevine, and it wasn't even a demonic grapevine. It was just a regular one, like Chamborsine grapes, I think it was. I don't know. But go subscribe to the channel, otherwise you might not see any demonic chess games, and you might not see whether or not. Oh, look right there. You might not even find out whether or not the planets are in control of solar flare activity. Hey viewers, thanks to everybody who's left comments and tuned in. Eugene,
yeah?
Anything else to say?
No, I don't think so. Like, sorry, it's kind of getting late, and I'm like, I'm just a little bit tired.
No, it's a delight. You're doing a fine job, and I think probably in a day or two you'll find yourself at 500 plus subscribers, as you're only 17.
Hopefully. Yeah, well, big thanks for everyone who's joined us, and thanks to Dan for streaming this. And yeah, maybe we'll do it some more. So check out the announcements.
Yep. Cheers. Anyway, we'll see you soon, viewers. Talk to you soon, Eugene. Don't be a stranger. And yeah, it's about that time. It's about time to make dinner. So